Okay, so we're gathering the last ones. Anyway, we can start. Hitoshi, this is last class. Then we have another class from Kevin, correct? Okay, thank you. And then we have questions at 4:30. And Hitoshi, if you can rejoin at 4:30 for the questions, it would be great. Otherwise, now you have 1 hour. Especially if you cannot join for the 4:30 question session, would be good to leave 10-15 minutes at the end for the questions.
Okay.
Okay.
So
Thank you
maybe
very much.
before I start, the one thing I failed to point out is that today I'm wearing the Muon Collider T-shirt, and also in the back, can you read it?
Most important message of the class.
More than lectures, I guess. All right. So we have been talking about how we can get a much better understanding of electric symmetry breaking using a high energy muon collider, or potentially also 100 TeV proton machine. And then we talked about how it may also require new physics like supersymmetry, technicolor, and extra dimensions, which helps us understand why such a thing as spin zero particle exists in nature to begin with, and how exactly that their masses are protected from a large potential radiative corrections. And then we basically came down the path of thinking about new physics opportunities that may become available at the 10 TeV muon collider. So now I'm following up on this question, we're broadly talking about what we might expect in terms of new physics. And obviously, the naturalness we talked about, in some sense, is a theoretical problem. And you may say it's only aesthetic issues. Theoretical problem, only aesthetic issues. But I just like to remind you one thing, that this naturalness argument actually worked before, and that was in the case of the cosmic inflation. Of course, I wouldn't say we have a firm observational evidence that inflation has happened. It has to wait for the observation of the tensor mode fluctuation in the density fluctuation, which may manifest itself in B mode polarization in C and B. And we can talk more about that later if people are interested. But the original argument for inflation was based on, for example, the flatness and horizon problem. And the flatness problem is based on the fact that if we have a radiation, like in the early universe, and then radiation would redshift like the scale factor to the fourth power, because each particle, the energy redshifts like 1/A, number density dilutes like 1 of the volume, and the product of them is basically the energy density. So that's why the whole thing dilutes as eta minus force. If you have non-relativistic matter, energy is given by the mass and it's fixed, while the density still gets diluted. So this also goes like minus eta minus 3. And that's the kind of the dependence on how the content of the universe gets diluted as the universe gets bigger and bigger. But if you consider a portion called curvature, this goes like only eta minus 2. And the curvature is this idea that if you have a three-dimensional universe, I can't draw 3 dimensions, I'm drawing 2 dimensions instead. You can have this kind of flat surface, but you can also have a surface of a sphere like our planet Earth. And in this case, it is actually a positively curved space, but you can also have a hyperbolic curvature like this one. So it actually extends bigger as you go out. So this is a negative curvature. And when the universe was born, it could have had any of these possible the geometries, and it didn't have to be flat. But given this A dependence of of the radiation matter and curvature, if all of them started actually more or less the same energy density initially, then quickly radiation redshifts. If there were non-relativistic matter at that stage, of course, that will also redshift. But curvature redshifts the most slowly. So soon enough, what you expect to see is a universe that is actually dominated by the curvature instead of anything else like matter and the particles in there. But that's not the universe we see today. The one we know from the CMB observation is the curvature contribution to energy density is basically less than 1%. So this picture is clearly wrong. What we need to draw is that right now, this is where we are. The curvature is the smaller component compared to matter and radiation. So what that means that when universe started out very small, right after the birth of its universe, then the curvature component must have been incredibly tiny. So if on the point when universe was born, if energy could have taken any form whatsoever, then why is the curvature so much smaller compared to, for example, the radiation? And if you think of the time when this was the temperature of 10 to 16 GeV or something, then the temperature and the scale factor goes linearly together. So what may be sort of similar to each other today should be different by a factor of 10 to the 16 GeV means 10 to the 20 EV. Current temperature is about 10 to the minus 4 EV, so 10 to the 24th. So this we 10 to the 46 in terms of the ratio. So compared to the overall energy density of the universe at the time of the birth, curvature must have been the 46 orders of magnitude smaller than the rest of the energy densities. And that was what was called the flatness puzzle. The idea of the inflation is that even if the universe may have started with a finite curvature like this one over here, if you exponentially expand it, then the curvature density would be suppressed by this exponential factor, and the radiation is formed after the inflation is over. So this is actually a renewed generation of radiation after the curvature got exponentially suppressed. So that was one motivation why people came up with inflation, namely to understand the universe being quote unquote unnatural, because we don't expect the curvature to be so small compared to other components, especially if you go back to earlier moments of the universe. And in order to dynamically explain it, that we'd rather rely on this idea of inflation, basically flattening the universe early on before the radiation was born. And also the idea of the horizon problem is that when we actually look at the CMB photons coming from all possible directions, and this is here we are, and then we know that you can observe this, the anisotropy in power spectrum, in the anisotropy in the CMB for temperature and polarization. And they're beautiful pieces of data. I'm sure you have seen those. And what this is telling us is that the fluctuation is only of the order of 10 to the minus 5 compared to overall temperature. And this region of space have emitted a photon that has just reached us. So they never had an opportunity to talk to the region over here. But then how could they arrange the temperature to be so exactly the same at the level of 1 part in 10 to the 5? And that is what is called the horizon problem, namely that regions of the universe which should not have been in causal contact, namely they are beyond the horizon, somehow seem to be the same. Somehow everything seems to be prearranged. And that was also another motivation for inflation, because when universe was born in the idea of inflation, it was actually less than 10 to the minus 26 meter. So the universe as a whole was a smaller scale compared to any other distances we have probed, even with the highest accelerator today. So that's an incredible, crazy idea to begin with. But inside this microscopic universe, basically people could talk to each other and they could agree on what temperature they're going to have afterwards. And then after they agreed on that, inflation stretched it out, and then they came into view only just now into our view, and we can observe the universe here, you can observe the universe there. But because they had all agreed on earlier on, even though this portion and that portion don't seem to be in causal contact today, they were initially. And that's how they could arrange themselves to have the same temperature and same density. And so that was the idea of inflation. And again, that was meant to solve some theoretical or aesthetic issues. But this is actually basis of all the agreement we see in this anisotropy in cosmic microwave background to the observation today, which is based on the idea of inflation. And you might also know the fact that if you actually look at this, the acoustic peaks, the quadrupole moment, which my colleague George Smoot took a very difficult task of observing for the first time, and of course he got Nobel Prize for it. But compared to the best fit data today, it's actually much smaller. And of course, people believe that it's due to what is called the cosmic variance, namely that we can observe only one universe, and the quadrupole moment here corresponds to L equal 2, which means LZ can take only 5 values. And these 5 values, each of them can have the statistical fluctuation. So by observing only few statistics, then you could actually have a fluctuation, which made the discovery so difficult. But how can you understand this little depression here? So if that is due to statistical fluctuation, this is the sum of all of these 2m squared. So you are adding these 5 components here. And all of them have to be, let's say, a third of what is expected from the usual, the best fit prediction. And getting 1/3 suppression for 5 of them is something like 10 to minus 3. So we are observing a little fine-tuned universe, even though the overall picture is overwhelmingly telling us this inflation idea seems to be empirically true. But the discovery was difficult because of this unfortunate fluctuation downwards for the lowest moment that George Smoot was looking for with the Kobe satellite. So we could well be in a similar situation in particle physics too. So if John Ellis is right that it's better to be late than never, then this may be the situation where it can be late. And our universe is a little bit fine-tuned. That's why discovering the anisotropy was difficult. In the same way, maybe our universe is a little fine-tuned about the electroweak sector, so that the discovery may be late beyond what we could actually do at the high LHC or possibly economy LHC. So even though this is a theoretical and aesthetic issues, at least there are precedents that something similar actually turned out to be true, more or less, modular discovery of the tensor mode in CME in the future. And that was actually also difficult, partly because of this little fine-tuning the universe actually happened to have. And that actually delayed the discovery of the anisotropy in cosmic micro background. So that's the one point I want to make. Now, if you move away from the theoretical issues, but rather look at empirical evidence or beyond standard model physics, we have 5 of them: neutrino mass, dark matter, dark energy, inflation, and baryon asymmetry. And you, I'm sure, are familiar with all of these things. In the case of dark energy inflation, we really have to rely on cosmic probes. In this case, C and B. B-mode polarizations. To observe the moment where universe was so small that even graviton went on quantum fluctuations. And those gravitons that come from the uncertainty principles end up burned into the density fluctuation of the universe today, becomes classical. because universe observes it. So the quantum fluctuation becomes classical. And classical fluctuation is supposed to be still here today as the gravitational wave background. And that gravitational wave background is supposed to jiggle the CMB photons to develop this specific polarization mode called the B mode. So that's the way we hope to actually observe the concrete evidence for inflation. And for dark energy right now, the main tool we have is the galaxy surveys. TeV is the one that has produced already many interesting data, which hints at the possibility that dark energy is not a cosmological constant, or maybe evolving as a function of time. I myself, I'm actually involved in actually leading another cosmic survey project called PFS, which is happening at a higher redshift. So that would allow us an uninterrupted measurement of dark energy, a function of time. So we hope to understand these things better on the way. And it's somewhat unlikely, I have to say, that the collider would shed any insight into either of these things, except for the fact that both of them seem to rely on scalar particles. So if the next generation colliders would give us any hints on why scalar particles should exist at all, I mentioned three possibilities just earlier this morning, and that at least help us to understand the context where we can talk about dark energy and inflation. So that's actually one thing we can hope for, but it's rather a qualitative input. In the case of neutron mass, as you all know, again, the cosmic survey is one way to get the spectrum of neutron masses. It seems to be normal hierarchy if you believe in TeV data, but it remains to be seen. Or neutron double beta decay. It could also be the case that the future generation of colliders can produce right-handed neutrinos, and people talking about that in the context of FCCEE from Z decay, for instance. So we may learn something from the future colliders. If the right-hand neutron scale is multi-TeV, again, 10 TeV Spartan center mass energy collider may have something to say about the right-handed neutrino, in particular, if there is a right-handed SU2 gauge interaction coupled to them. And again, that's no guarantee, but that's actually something we can look for. And to what I'd like to spend the rest of my time on the two remaining things, dark matter and baryon asymmetry. And dark matter, I'm sure everybody knows, has a firm evidence from the rotation curve on a galaxy that the rotation speed seems to be more or less constant on the outskirts of the galaxy. So compared to what you would expect, like one of us where we are, which is what we learned in high school from what the gravity is supposed to do in Kepler motion. So this rest has to be filled by dark matter. That's the evidence on a galactic scale. I'm sure you have seen also the pictures of the clusters galaxies where you might see some giant arcs of the distant galaxy, which looks really, really stretched by the gravitational lensing effect. And also in this micro background, anisotropy and overall height of these peaks basically shows the depth of the gravitational potential at the time of recombination. And all of them point to the same idea that the dark matter of the universe, which is not made of ordinary matter, is something like 25%. And we have gone through every possible candidate in standard model to see if any of them would work, rather than trying to introduce new objects to speculate on, and everything failed. Neutrino is actually a component of dark matter, but it's too light to be the dominant component. The people talked about also dim stars and black holes. They don't work, except for the possibility of primordial black holes, which is already speculative in the sense that you assume certain black holes could have been formed while universe is still radiation dominated and hot and relativistic. And you can come up with such a scenario, but it's already beyond the standard model physics if that actually turns out to be the answer. But now we are talking about also the possibility that they may be elementary particles. like WIMP, or very light wave-like particle. We talked about Bose-Einstein condensate earlier this morning. So it's meant to be Bose-Einstein condensate or very, very light particle whose Stokestheory wavelengths really overlap within the galactic scale. And one prime example, of course, is the axion. And so the WIMP has been around already for a long time. And before my time, I think that they started back in the early 80s. I wasn't there back then. And it was already a paradigm when I got into the field. So it has been talked about for a long time. And people have been looking for it for many decades. And here's the mass and the cross section. I'm sure, again, you have seen these plots that the limits are getting better and better. And here's the neutrino floor, where even the neutrinos end up being the background. So we're actually reaching to that level now. And where I started, when I got in the field, people are still talking about, for example, heavy neutrinos as a potential dark matter candidate. And we have gone down like almost 20 orders of magnitude since then. This is an incredible feat. And the reason why we're talking about the mass range from, say, 10 GeV to 1000 GeV here is because of this coincidence sometimes called WIMP miracle. So if you assume that WIMP was in thermal equilibrium at a high temperature, but reduced their number by its annihilation process. And here is the mass over temperature, so time goes this way. And here is the yield, which is energy density over the entropy density. And when the particles were resisting in thermal equilibrium, this is basically order 1 here. But when the temperature is below the mass of this particle, then the number density in equilibrium should be suppressed by the Boltzmann weight. But the Boltzmann weight means not only that it is actually in equilibrium due to the interactions among them, its number also need to decrease in order to go with the Boltzmann suppression, which requires a process. The number of WIMP can get lost. Without such a process, then this curve can never be followed. And that's why we are talking about this kind of annihilation process. So as long as this annihilation process is happening faster than the expansion rate of the universe, then the number density of this WIMP particle just keep following this Boltzmann curve. But once the universe gets big enough, and once WIMP number starts to decrease enough, then at some point they will stop finding each other. They cannot find each other anymore. And then they can no longer annihilate to reduce the number to follow this Boltzmann curve. And that's when the number density freezes out. So that's the picture we talk about when we talk about the weakening rational density particle as a dark matter candidate. So when this freezes out, and what is the number density you end up with, obviously it depends on how strong this annihilation process is. As a matter of fact, the total contribution to energy density today is inversely proportional to the annihilation cross-section. And if you go through the math, it turns out that annihilation cross-section, which is something you might expect at the electroweak scale of the weak-ish coupling constant, like fine structure constant, and some electroweak scale mass, like 300 GeV, turns out to give you the correct abundance of dark matter today, and that's what we call the WIMP miracle. Especially in view of the fact that we were hoping to observe new set of particles like supersymmetric extra-dimensional compositeness that would explain the picture behind this electroweak symmetry breaking near the electroweak scale. So hoping for a new particle at that energy scale appeared very natural in that sense. And that's why there have been high hopes that WIMP could be the right paradigm to understand the nature of dark matter. And as I said already, the people have been searching for a long time. We have not been able to see it. So some people start to think that, well, this is already discredited. WIMP is no longer the case, and start to pay attention to axion and other potential directions, which I'm guilty of doing that myself. So certainly we can look elsewhere too. But if you just again take a broad look at what WIMP might be, and at least this idea makes sense, it seems quite natural as long as there are new particles at the 100 GeV, 1 TeV energy scale that would actually give you the correct abundance at the end of the day. And given the fact that we are not talking about, for example, supersymmetry already in multi-TeV scale instead of below TeV scale, what that means is that the SUSY breaking scale is already quite a bit bigger than the electroweak symmetry itself. Then what you can talk about as a SUSY particles is they are supposed to be close to weak eigenstates. And that is actually a new regime which appears actually in this region, which had not been probed actually as much, even in direct detection experiments, and also searches at the LHC. So let me explain what this being close to weak eigenstates mean. So in the case of supersymmetry, we talk about neutralinos, which is a mixture of the superpartner of the hypercharged gauge boson, namely BNO, superpartner of the W boson, we know, and we know is an SU3 triplet, so there's actually a neutral component to that. And in supersymmetry, there are actually two Higgs doublets. Both of them have the fermionic partners, and both of them have the neutral components. So these are the Higgs xenos. And they all mix. So if you write 4x4 mass matrix, the BNO may have mass of its own. We know may have mass of its own without having regard to the electric symmetry breaking. And Higgsino is a Dirac fermion, so it can have a mass which is off diagonal this way. But what can happen here is that you may have contribution from electric symmetry breaking in these off diagonal entries because the Higgsino can turn into Higgs with we know, for instance. This is a superpartner of SU2 gauge interaction. Excuse me. And once this Higgs acquires an expectation value, that will give you this mixing mass between Higgsino and we know, and that fills in these components over here. And same can happen also for BNO. So their mass matrix actually looks like this. And when people talked about the WIMP in this mass range, then they could have been pretty well mixed between these gaugino components and Higgsino components. But this picture is now different today because we're now thinking about these parameters which break supersymmetry to be larger than the electroweak symmetry breaking scale. Then once you actually ignore them more or less, then you're talking about these states, BNO, we know, Higgsino, Higgsino, to be very good approximation to mass eigenstates, because these off-diagonal ones are somewhat negligible compared to these ones along diagonal. So that is what I meant when I said close to weak eigenstates. And the point is that when they're close to weak eigenstates, their detection becomes actually more difficult. So if you have, for example, this we know state, we know that W plus W minus can couple to Z. Correspondingly, its superpartner can couple to Z. And that would actually create a relatively big interaction to the ordinary atomic nuclei. But we also know the third component or neutral component does not couple to Z because this coupling is proportional to epsilon ABC. If A, B, and C are the same, that's identically zero. And that's just follows from the SU2 group theory. So when you have a dark matter, which is small as pure we know, then its interaction to the standard model all of a sudden becomes actually very much suppressed. And then we know, like dark matter, can well be in this neutrino floor, which is very difficult to detect. At the same time, because this interaction is very a pure state, the annihilation can be also predicted fairly reliably, and W3 can go through W plus minus into W plus W minus states, and this reaction can be computed and then predict the abundance. It turns out that there's also the binding effect you need to consider, which is called the Sommerfeld enhancement. Yes. Oh, okay. And somebody came in, but hopefully it's okay to continue on. And so that actually tells you that additional non-perturbative effects you have to take into consideration, but that has been actually understood quite well today, originally due to technology and Matsumoto. And so that actually predicts the Reno mass to be about 3 TeV to give you the viable dark matter abundance. So instead of being here, it's actually there. And that actually makes it even more difficult to detect directional in direct direction experiments. So, but on the other hand, because this particle has an electroweak interaction, so if you have a collider of enough energies, you should be able to make them. So at least these guys can be directly produced from Z if you couple this to, let's say, mu plus and minus in this direction. So you should be able to produce them, and W plus can decay into very soft, for example, electron neutrino and W0. This could be also pion in some case. And you are looking for these very soft particles coming from this charged state decay to neutral state. And these very soft states are very difficult to pick up in the hadron collider environment. But in lepton collider environment, I showed you some of the event displays yesterday, these things can be picked up. So as a matter of fact, if you actually look at any of the typical plots you see from the LHC experiment, you are typically looking for some SUSY particle that's heavy, decaying to something that's light. And here's the line where they are degenerate in their mass. And typical exclusion looks like this, so that heavy particle can decay into light particle with enough of the phase space available so that decay products are energetic enough to be picked up in detector. But in this case, because the state is fairly pure weak eigenstate, and under SU2 gauge symmetry, neutral and the charged ones, of course, degenerate in their masses. Their masses are split only by the small radiative correction, which you can compute. And so you know how soft these particles are, and that looks very difficult in hadron collider environment. In principle, you can also look for a long-lived particle that is disappearing inside detector and so on and so forth. If not, it's not hopeless, and I certainly encourage experimentalists to keep continuing their effort, but at least it's just not easy. And for 3 DV particle, that's already beyond the reach of the hydromer LHC as well. And so for the small energy gap to be detectable, you need to reach very, very close in to filling the gap to very small mass differences. And for that, lepton collider environment is actually very useful. So this is sort of the different kind of the search strategy people talked about in days of LEP, where states are fairly well mixed with each other, and they're big enough phase space for decay, and that actually made the signal rather easy to pick up. But now in the regime where supersymmetric particles are heavy, you expect them to be close to the weak eigenstate. That makes this phase space in decay very small, which is very difficult to pick up. But the lepton collider environment, like mu plus mu minus, would allow you to actually do that. So that's yet another reason why lepton collider could be actually very beneficial to extract more information from data, even though total cross-section is much smaller compared to those in hadron collider experiments. And so here I focus only on Wiener, which actually may be already excluded by looking at the gamma rays coming from the galactic center. And there has been recent studies by Ben Safdie, one of my colleagues, about this. But it certainly depends on the density profile in the galactic halo and so on and so forth. So I don't think the verdict is already there yet, but at least you see the idea how this kind of state would make the search in lepton collider much more important. And it doesn't have to be Reno. It could be actually Higgs-Xenos too. And Higgs-Xenos mix this way and to a Dirac fermion. And if they do form Dirac fermion, and they again have an interaction of H up going to Z like this one. But if you include this tiny mixing due to these off-diagonal elements in the mass matrix due to electric symmetry breaking, they actually end up forming into plus minus linear combination to become Majorana fermions instead of Dirac. And this kind of situation is called pseudo Dirac because very close to Dirac fermion, but two mass eigenstates states are split just by a little bit, so that each of these states are Majorana on their own. And once they become Majorana, then this coupling is velocity suppressed. And therefore cross-section is suppressed by the, sorry. Velocity squared, and therefore again, the direct action becomes difficult. In this case, we're talking about something like 1.2 TeV for the Higgs-Xenon-like dark matter. And again, that's beyond the limit of what we can hope for at the LHC Large Hadron Collider. But once again, if you have multi-TeV lepton collider, this is also an easy target because you can produce, I wouldn't say easy, but you can produce the charge states which decay into neutral state, again, with a small phase space. But I talked about already that these small the phase space for decays can be something you can pick up in principle. So in the event display, that would probably look something like this. You have a collision. It looks almost empty, but you have a track that may be looking like this for pi plus and pi minus, where the charged Higgs xeno against the neutral Higgs xeno with a very low momentum pion. Because it's low momentum, that curves around quite a bit in the magnetic field, very low energies, but you may be able to pick them up because there's nothing else going on in the event, so you can actually see them rather clearly. So that's the idea that we may do better looking for the dark matter particle in the lepton collider environment. So this is definitely a case for building a lepton machine that can go into multi-TeV so that you can pair produce these particles. So in this case, 2.5 TeV, TeV is the minimum. In this case, it will be 6 TeV is the minimum. And once again, you have 10 TeV that would give you ample room for actually missing something. And so that we can be sure these particles do not exist. So in some sense, the 10 TeV muon collider will be a place to definitively exclude, close the WIM paradigm. And of course, definitive in this case may have some loopholes if you're thinking about some particle whose SU2 isospin, so the quantum number on the SU2 left may be much bigger than a doublet for Higgs-Xeno or a triplet for Wiener, something much bigger like the 5-plet and the 7-plet and so on and so forth, then you can actually have heavier masses, which goes beyond the reach of the muon collider. So it is not that it doesn't have any loophole, but we have again not seen the particles with a very big quantum numbers under the gauge group so far. So if you stick to some of these low-lying representations of being doublet or triplet, certainly even without thinking about supersymmetry at all, that can still be the dark matter candidate, and those particles can be definitively excluded by 10 TeV muon collider. So that's the reason why this is also a very interesting direction to pursue. Okay, finally, baryon asymmetry. So everybody knows that in order to explain the baryon asymmetry universe, you need to satisfy three conditions. Because we need to create non-zero baryon number, we need to have a process that violates the baryon number. And universe needs to pick whether to produce more particles or more antiparticles. So they need to be able to differentiate between particles and antiparticles that would require violation of C and CP. Finally, in order to actually have a process which is not in detailed balance, namely that even if baryon numbers can be violated, even if CP is violated, but if everything is homoequilibrium, a process that can go into the direction of producing baryon asymmetry will be in detailed balance with its inverse process of eliminating the baryon asymmetry, then there's no gain. So that's why you need to have a departure from thermal equilibrium to achieve the production of baryon asymmetry, namely baryogenesis. And within the electroweak the theory, the baryon number is actually violated. B minus L is conserved, but baryon and baryon number can be violated by the same amount as the lepton number. And I'll tell you how that works on the next slide. We already know that C and CP are violated in nature. And this Kobayashi Kabibo Kobayashi Maskawa phase is one example of that. There could be more CP violation in neutrino sector people are looking for, but at least we know CP can be violated. And a tricky thing is this departure from thermal equilibrium. And one thing people did talk about is just like the boiling water. When you have a pot with water in there, and if you put that on a heat, on a gas oven, then you start to seeing these bubbles forming, and then eventually that would pop and evaporate into the air, and that's how water boils. The point here is that the bubble is filled with gas phase of our vapor phase of water. The surrounding is the liquid water. So you have the coexistence of gas and liquid happening in this boiling water, which means that it's not in thermal equilibrium. They coexist, but they are not in equilibrium. As a matter of fact, being in equilibrium means nothing changes over time. But if you keep boiling water, then of course you see more and more water molecules evaporating into the air. You see less and less water. So it does change over time. So it means it's out of equilibrium. So namely that in general, if we have a first order phase transition, you can have coexistence of two phases of matter, which is out of equilibrium. And the hope is that you might be able to use that to create baryon asymmetry. In particular, the idea called electroweak baryogenesis. This is the idea that when universe started out with symmetric phase and turned into the symmetry breaking phase, you may have a first order phase transition that universe first form bubbles with the non-zero expectation values while outside expectation values to 0. And once these bubbles form, they start to expand, and eventually they would hit each other, and bubbles fuse to become bigger bubbles, and over time, all the bubbles fuse together so that the entire universe gets filled with what's inside this bubble, namely the electroweak symmetry breaking state. So that's actually one possibility the people can conceive. But in order to achieve the first order phase transition, you need to have a potential that actually change over time in the following way. So here's the Higgs field, here's the potential. And initially, it looks something like this. But then you need to see how this potential can become like this. And this portion keeps coming down. And this and that become degenerate. And then it becomes lower. At this point, the universe can start tunnel from here to there to start forming these bubbles. And then eventually you find all of the universe to be in this state over time. And this is the way you can jump from zero expectation value to final expectation value rather than following a continuous curve like what we know for the magnetization in the Heisenberg ferromagnet. So here, this is an example of second order phase transition. Your magnetization is zero and start to turn on, but sorry, something is wrong again. So the expectation value is zero, but then start to turn on like this one, but there's no discontinuity, changes only continuously. But in this case, you jump from zero expectation value to final expectation value by tunneling. So there's discontinuity. So change of the wave as a function of temperature looks like it's zero here, and then there's a jump, the discontinuity over here. And that discontinuity allows for these bubbles to exist, and the bubble walls are moving and expanding. And in this phase with no expectation value, you have many massless particles, and those massless particles can bounce and reflected by this expanding bubble walls, and that interaction may pick up CP violation in some way so that it can create a symmetry of delta V being non-zero as a result. And in the case of the electric paragenesis, people have studied this in great detail in the context of the supersymmetry, and it's looking very difficult because the way to actually achieve this shape of the potential would require a loop of particle inside this Higgs expectation value, which is massless when expectation value vanishes. And there was even such candidate, the scalar top. It could be massless when you turn off the Higgs expectation value, but becomes heavy when you do turn it on, as heavy as the top quark mass itself. And loop of particle like this one could have actually produced this shape. But then that would actually predict 170 GeV scalar top, which is, it looks like it's already excluded. So it doesn't work in this context. However, you can have a potential with usual phi squared and lambda phi to the fourth. And I told you already that lambda being bigger than zero is what gives you stable universe. But just for the sake of the argument, imagine that lambda actually might be negative for the moment. Then it may be unstable. But the potential may actually look like this. So it starts to rise with phi squared if this is positive. Again, that's not what we normally assume in the standard model. And lambda phi to the fourth would make the potential go down at a larger amplitude. But just suppose it may be stopped by phi to the sixth term so that it turns around again if k is positive. I didn't write 6 here. It's meant to be 6. And of course, the phi to the 6 is not a renormalizable interaction in the standard model Lagrangian, so we normally don't write it. But it could be generated as an effective operator if you have, for example, Higgs interacting with some singlet scalar. And if the singlet scalar has the cubic interaction on its own, then this eventually, after you integrate this singlet particle, would produce a potential that looks like this. So maybe this is how the Higgs potential value can be understood. Looks like a very different mechanism from what we assume in the standard model, but at least it's not forbidden to think about that. And if this were the case, And as the parameters change, as the temperature changes from the early universe, it might have been this shape. And then you may start seeing the impact of 5 to the 4th, and then eventually come down here. And that is the way of producing first order phase transition in a different way from relying on this loop of the nearly massless particle. So that idea can still be viable. And if that is the case, the measurement of the Higgs self-coupling would be really crucially important because that can really show order 1 deviation from the prediction in the standard model. So that's another reason why just the minute you start thinking about the physics beyond the standard model, given that we have so many empirical evidence that we actually do need physics beyond the standard model, and especially in the context of dark matter and baryon symmetry, there are at least well understood, well described models out there that would predict important signals of producing new particles in 10 TeV central mass energy collider, or seeing the anomaly, big deviation in a Higgs self-coupling, which is connected to the issue of the baryon asymmetry. So that's pretty much all I have to say today. So we started actually talking about the understanding electrocentric braking as a paradigm, trying to actually go well above the scale to look down on it so that we have a full understanding in a similar way that we understand QCD scale by looking down at it from, for example, lip data, looking at the very precision measurements of the jet properties and their interactions. We hope to get the same level of understanding. That's why we need to go to high energy. But in addition, the whole argument of naturalness and trying to put a context in the spin zero particle gave us extra motivation to look for new physics at high energy scale. And in addition, we have these empirical evidence for physics beyond the standard model, at least 2 of which would suggest that there could well be new phenomena you can observe the 10 TeV per center mass energy colliders. So at least there are many good reasons to actually argue for it, think about it, and therefore we should like to design it and do an R&D to demonstrate the technology, and eventually, hopefully, we get to build one to observe all this fantastic physics we are talking about today. Okay, that's it. And I stop here and respond to questions you may have.
Thank you very much, Hitoshi. Questions?
Sorry, there are other people in the business.
I have one in the back. Just one moment.
Thank you, Hitoshi, for the awesome talk. I have a question about the WIMPs. So you were talking about the SUSY neutralinos as the WIMPs. Are there other BSM particles also, other than SUSY particles, which can act like a WIMP?
Yeah, so I briefly mentioned this. So I talked about Reno and Higgsino in the context of supersymmetry, but it doesn't have to be. What Reno needs to be is just SU2 triplet fermion. And that's all it takes. So once you actually have an SU2 triplet fermion, which is basically the same thing as we know, and then everything I talked about today would basically carry over to that case too, whether you think of it in the context of supersymmetry or not. And same with the Higgsino-like particle. If you have this Dirac SU2 doublet fermions, which may get split just by tiny bit by mixing with the other particles, other high masses, and that's again good enough. It doesn't have to be really Higgsino in the context of supersymmetry, but it's so random isospin 1/2 SU2 doublet fermions. And one can even think about other possibilities that it could be even some composite objects too. It doesn't have to be even elementary. So as long as they can have the electroweak scale interaction with electroweak scale masses, it would qualify as WIMP. And if that electroweak scale interaction is really electroweak within the SU2 goes to 1, you have a big cross section to be able to produce these particles at colliders. And once again, this argument doesn't rely on supersymmetry at all. In fact, the extra dimensions also provided candidates for WIMPs out of these Kaluza-Klein towers I mentioned earlier. So SUSY, compositeness, extra dimensions, it doesn't have to even be connected to these natural issues at all. Just having additional particle charged and electroweak quantum numbers on a multi-TeV scale would probably fit the job.
Okay. And so recently there was this LZ results, I think in February.
Mhm.
Did they, I think they have put a very stringent limit on the WIMPs. So
Mhm.
did they put the limit on the WIMPs or just the SUSY particles which act like WIMPs?
So it turns out that the kind of candidates I talked about today are still well below the limit they managed to produce. And I have to emphasize that the limits are incredible. And the fact that they have been able to go 20 orders of magnitude below where they started is really, really amazing. I have to emphasize that. But nonetheless, the kind of parameter space you're talking about for these WIMPs is really at the top of the neutrino flow or below. So direct detection experiments would have a very hard time actually digging this much in the midst of this big background coming from neutrinos. So that's an unthinkable situation, but that's where we're getting to. And so even the amazing LZ limit actually doesn't exclude this possibility.
Okay. Okay. Thank you.
Any more questions for Hitoshi? I don't see questions for now, so we'll check on the document later in case you can join. And otherwise, we take the opportunity to thank Hitoshi once more.
Okay, so I try to come back at 4:30, but I
Yes.
can't guarantee it. Again, because I'm at the hospital right now. I don't know how things go. So
Of course, no problem. Hope to see you in person soon at some point.
okay, I hope so too.